All right. Hi, everybody. Today we are going to talk about inverses, section 6-7 in the textbook, for those of you who are keeping score. Yeah, here we go. We are going to talk about what inverses are. We're going to talk about finding inverses. We're going to talk about what graphs of inverses look like. We're going to do some practice finding inverses, and then you're going to take a mastery check. It's a straightforward sequence of things to do today. All right. Learning target 6C is about composing functions, which is something that we worked on last lesson. And then the other part of this is to find inverses of functions using composition. So a couple of things there. What is an inverse? And the inverse is sort of an idea that I don't think you have seen a whole ton of. And so here's the idea of an inverse. Normally, and I think this diagram is helpful, but maybe it's not for you. Normally we start with an input. And we go sort of, I think you've probably seen these kind of function machine diagrams where you go through this box called the f of x machine and you get an output right here. That's what we normally do with a function. An inverse function, or an inverse, takes the outputs, puts it back through this thing called the inverse, and gives you the inputs. So the idea here is that if you start with inputs, you go through the function machine, back out through the inverse function machine, you'll get the inputs back. So that's exactly what this is saying. And there's a composition symbol right here. So we'll have to kind of think about a little bit about what is a composition symbol telling us, but here's the deal. If you take a function and you compose it with its inverse, that's what this f to the -1 is. We say f inverse. If we compose f with f inverse, the function is just x, so the thing you're putting in is x. That's what this part says. You're going to get the input back out. And the other part of this equation right here is this, and this just says you can do it in either order. So you can either do f composed with f inverse like this, or you can do f composed with f inverse like this. Either way, you will get x out. So you're going to get the inputs back out. All right, so that's a lot of words to say a kind of simple thing. What we're doing is we're starting with a function called f. We are going to create a placeholder for what this f inverse is, put it in, and see what we get out. So we want f composed with f inverse to give us x. So if we know that f of x is this thing, to compose it, we're going to take that f inverse of x thing and put it in for x right here. Our output needs to be x. So to find f inverse of this, we're going to take the composition of f inverse with f. So we're going to write 3 minus, we're going to take that f inverse of x, which we don't know what it is yet, but we're going to put it where the x is. The output of this process needs to be x because that's the definition of an inverse. When you compose a function with its inverse, you have to get the inputs back out, which is x. Okay, now we can solve for f inverse of x. And so to do this, we can subtract 3, subtract 3. So now we have the negative inverse of f is equal to x minus 3. I have the -1 here. I want a positive one, so I'm going to divide both sides by -1. And then I get, okay, so now the f inverse of x function is -x plus 3. I took this part and divided it by -1, and then I took this part and divided by -1. And this is my answer here. Okay, so that was a lengthy process. But I want to talk about what we're really doing. What we're really doing is we're taking the inputs from one function and making those the outputs of a new function. And we're taking the old outputs and making them the new inputs. Remember that sort of four-sided chart where we started with in and we ended with out. We had an f of x here, and we had our f inverse of x here. I'm sorry, that's so small, I should have written it bigger. But we're taking, to find this inverse thing, which is this, we're starting with the outputs and going to get the inputs. So this is sort of a new idea, but it's not that wild here. Really what we're doing is we're taking the roles of x, which are usually our inputs, and making those the outputs, which is usually what we choose for y. We're choosing the y's, which are the outputs usually, and making those the x's, which are the inputs. So if we think about what we're doing on the graphs, we're exchanging the x values for the y values and the y values for the x values. So any spot on the graph is x, y. But this point right here is almost like the point y, x. So this is a little bit weird, but this is what I'm saying is we're taking the x values and putting them in where the y values usually are, and taking the y values and putting in the x values where they usually are. Okay, here are two examples of two functions. And so this function is, this function is f of x. That's this red line here. And this is the green line right here. These two functions are inverses of one another. And the thing that you need to know is that inverses are reflections along the line y equals x, which is this dotted line that I'm pointing out right here. So I'm trying to kind of explain this whole thing, which is pretty abstract, pretty weird, pretty like strange to just think about, but there is kind of a nuts and bolts process for us to do this. When I say we're switching the outputs and inputs and their roles in the way these functions are working, what that really means is you can change the x's into y's and the y's into x's, because that's what an inverse does, is it takes the outputs and makes them inputs, and it takes the inputs and makes them outputs. Okay, so normally we've been working with function notation, which is f of x or g of x right here. Your steps are going to be to rewrite the function with y equals, because one, we're a little bit more comfortable with y, and I recognize that, but also this just allows us to choose to change the x's into y's and the y's into x's. So I haven't done anything except for rewrite it with a y instead of a function notation. Because we're taking the inputs and making them outputs, you can change the x's into y's and the y's into x's. So now, this is the part where we invert the function. And so what we're doing is we're taking those inputs, making them outputs, just by changing where the variables are in the equation. The next step is to get y by itself, because we're really comfortable with graphing things that say y equals. And so we want to do that. The problem is sometimes that can be a messy process, and I'm going to show you why that's messy in this example. Most of the ones you're going to do in this year are truly not this messy and not this difficult, but I do want to show you one of these kind of more difficult ones just to get started with the day, and then we'll kind of dig into the ones that are going to be more like what you're going to see on the homework. So now at this point we have to solve for y. And doing this in this problem is one of those ones that's a little bit difficult. And so what we're going to have to do is we're going to have to complete the square. So this is a throwback to first semester. The reason I have to complete the square is because I have a b term in this quadratic, and it's not easy for me to just get y by itself. It's also not one of those situations where you can solve using the quadratic formula or something like that, because we're not equal to 0 here, we're equal to x. So we're really rewriting this equation a different way, and so we need to use completing the square to get there. Normally we would do y squared, Normally in the box, we would have our y squared here. We're going to split our y term, this b term here, into even parts, negative 2y and negative 2y. On the outside of the box, then, we would have our y and our negative 2 on both sides, which would mean I have to have a positive 4 here. I don't have positive 4 here, I have negative 12. So to get to positive 4, I need to add 16, but I have to do it to both sides. Maybe you see where this is going now. I can rewrite what I have on the right side of the equation now as y minus 2 quantity squared. What I have on the left side of the equation is x plus 16 now. And now this is a situation where I can solve for y. So if I solve for y, I get, so I'm going to take the 2 square roots of y of this stuff inside, or I guess of both sides of the equation. And we're going to end up with plus or minus the square root of x plus 16. Then we need to add 2 to both sides. And this is a little bit tricky, but you just have to be careful about how you write your square root. So it's x plus 16. Then I like to write a little like corner on the square root to say the square root is over now, and then I write plus 2 here. On this side we get y. So we have now a square root equation, which is the opposite of, or the inverse, excuse me, not opposite, inverse of g of x. So we can write g inverse is this stuff. The thing about inverses is the language is really difficult. There's a difference between the inverse of a function, which is what we did in the last example, and the inverse function. So the words of a are really, really important here, and that tells us something specific about an inverse. We're going to dig into a little bit more of this next lesson, and I just wanted to kind of say that this is an important thing, but we'll talk more about why it's important tomorrow, next lesson. We're really focused on the inverse of a function today. The inverse functions we're going to talk about a little bit more tomorrow, our next lesson. The reason we care about this is because maybe you're just kind of thinking about what the graphs here of these things look like, but we had on that last example, we had a parabola, which was g of x. If we take that and reflect it across the line y equals x, we're going to get the graph of the inverse of the function. And so that's going to look something like this. And I'm not going to be perfect here, but what you might notice is that this is not a function. It fails the vertical line test. So there are 2 places where a vertical line crosses that graph, and that means it's not a function. So we have to do something about that, and that's why we're going to talk about that next lesson and not today. All right, let's do another example of finding an inverse of a function, and then we'll do a little graphing here and just see what we can come up with. Let's start by just putting in these values for x in f of x, see what we get out for a minute, and then we'll go from there. So the first one we would put in 0. So now we have 0 minus 2, which is the square root of negative 2, which is not a real number. So we can write DNE for does not exist. If you put in 2, you get 0. Square root of 0 is 0. We would get the square root of 1 here, which is 1. Square root of 2 here is about 1.414-ish. The square root of 3 is about 1.732. And then the square root of 4 is 2. So we can graph these points. This one doesn't exist, so we can't do anything about that, but we can do these 5, I guess, points. All right, so here they are. 2, 0. 3, 1. 4, 1.4. 5, 1.7. 6, 1.62. There we go. So this square root graph looks something like this. We'll dig into this a little bit more next week too, or later this week. Remember that really I can take that graph and reflect it across the line y equals x, which is like this. And so now this point goes here, and this point goes here, and this point goes here. Excuse me, it's like this. Something like that. And now we can see that this is kind of 1/2 of a quadratic. So now let's calculate f inverse of x, and we'll see what we get out. So we're going to put in y, and now we're going to switch. To invert, we're going to switch the x's and y's. Okay, so to do this, we need to solve for y, we need to square both sides. So now we have x squared equals y minus 2. Then we need to add 2 to both sides. So now we get x squared plus 2 equals y. And if you think about this, this is a vertex form equation with the vertex 2, 0, 2, which is this point right here. So this looks like it should have this other half over here. So why doesn't it? That's something we're going to dig into a little bit next week, or next lesson. I keep saying next week. All right, so quickly, if you put in 0, you get 2 out. If you put in 2, you get 6 out. If you put in 3, you get 9 plus 3, 9 plus 2 is 11. 16 plus 2 is 18, etc. So f inverse is this function here. And we can see from that the graphs are reflections across the line y equals x. This is more of kind of the same idea as what we did on the last slide. I'd like you to start by graphing these two functions and just confirm, are these really reflections across the line y equals x? I'm going to sketch the line y equals x on the graph here. It looks like this. You sketch those other two lines on the next slide, and then figure out, does this look right? Are these inverse functions? Okay, so I want to go back to this pair of functions, and we graphed these already. And so just real quick, this square root of x plus 2, x minus 2 looks like this, or something like that. And then this is a parabola that we're comfortable with, where it'll look something like this. Okay, so there it is. All right. What is the domain of f of x? F of x is this one. So the domain is the set of things you can put in to a function. So I'll write set of input values. What are the things you can put in for x in the function f of x? You can put anything as long as it's greater than or equal to 2. So x has to be greater than or equal to 2. And I'm saying that because if you put in a 1, or if you put in 0, or if you put in -1, anything over here, first of all, the thing is, the graph doesn't even start over there. So the graph starts right here and goes to the right. And so all of those values are all defined, and so we can figure those values out. But if you put in something like this, you're going to get an error in your calculator. So that's how I know that x has to be greater than or equal to 2. Let's think about the range then. The range is the set of output values, which means the things that you could get out of the function when you put the stuff in. So what are the outputs? Well, they're the y values. What are the y values you can get out? Well, you can get anything greater than or equal to 0. So you have to say y is greater than or equal to 0. Now this is the tricky thing about this inverse function thing. Because what we said was, we said the x values and the y values trade roles, and the y values become the input values and the x values become the output values. And so we could say now that when we look at the inverse function, the domain is x is greater than or equal to 0, because we're taking this range that was the set of output values and making it the set of input values that you're putting in. And we can take the same information about the domain of the original function and rewriting it as the range of the other function. So the range is y is greater than or equal to 2. So what does this all tell us? Well, it says that really the inverse of the blue function, which is this one right here, the inverse of this function is really only this half of the parabola, because this is the spot where x is equal to 0. And since our domain says x is greater than or equal to 0, we have to chop off this other half of the graph. So this part is not technically not the inverse. This part over here, the left part, is not the inverse, but the yellow part is the inverse. So this is sort of part of that distinction between the inverse function and the inverse of the function. This is the inverse of the function, but the inverse function is only this part. It can only be this part because only this part of this graph is defined. That's a whole lot of talking to just say you have to chop off one half of the parabola. But it is important that you understand why can we say the domain and the range are certain things, and then how do we translate that into the domain and the range of the inverse of the function. All right, so let's start with a new function. Let's call f of x this weird, what's called a rational function. We're not really digging into these that much this year, but it is a kind of an interesting kind of function. But what I need to think about is, what values can you put in for x? Can you put in everything, or are there limits? And the one thing I know is that if you have something that looks like 1 divided by 0, this is undefined. And so anything I put in that makes the bottom of the fraction 0 makes the whole function undefined. And so we have to say x minus 1 cannot be 0. Well, if you solve this non-equality almost, you can say, well, x can't be 1. So the domain is everything, all real numbers, except x equals 1. So it could be everything you can put in. You could put in negative 17,000, or you could put in negative 47, or you could put in 84. You could put in anything except for x equals 1. If you put in x equals 1, then you get an error. The range is a little bit tricky here, because if you think about what this graph looks like, we don't have any instincts about that. But one thing that we can do is we can think about, well, what happens if you put in a couple of different values? If you put in negative 14 million, that's just an example, for x, you're going to get such a tiny number in the denominator that it's going to be 1 over 14 million, negative 14 million, and 1. That's such a small number, and it's so close to 0, but is it 0? No, it's not 0. If you put in a huge number, like 12 million positive, you're going to get the same thing. You're going to get some number that is super tiny, but it's not quite 0. There is a fancy word for that, and I'm going to introduce that word later this year. But here's the thing. This is just saying the outputs, anything you put in that's really big can't be 0. You're not going to get 0 out. The outputs you could put in, if you put in like -1/2, you'd get -3/2 in the denominator. 1/3 is 2/3. You could get some kind of other fraction. You can get all these other numbers except for 0, and you can confirm that in the graph. The graph is going to look something like this, I believe, and you're going to see that there's a spot here where this graph cannot touch. So that's kind of interesting. The range is all the output values, and we know that the outputs cannot be 0. So we could say all real numbers except y equals 0. I guess is the way we've been saying this. So all real numbers except y equals 0. All right. So now let's find the inverse function, the inverse of the function. And so what I'm going to do is I'm going to rewrite y equals 1 over x plus minus 1. We're going to reverse the places of the variables. So we're going to put x here and y here. I want you to get y by itself. Here we go. To get y by itself, we're going to multiply both sides by y minus 1. And we're going to end up with, I'm not going to distribute this yet, -1 times x. And there's a really good reason for why I'm not distributing it yet. And then we have 1 on this side. If I divide both sides by x, then we get y minus 1 equals 1 over x. And then if we add 1, we get y equals 1 over x plus 1. This is the inverse of the function. Okay, so that's good. We've done that. Now we need to do a little composition here. Let's take the first composition here. We're going to put in 1. We're first going to put it in for x in f inverse. Then we're going to take the result and put it back in to f. So f inverse of 1 is, okay, 1 over 1 plus 1. So 1 over 1 is 1. 1 plus 1 is 2. Okay. Then we're going to take f of 2. F of 2 is 1 over 2 minus 1, which is 1 over 1, which is 1. So f composed with f inverse of 1 is 1. What happens if we do the opposite order? What happens if we put it into 1 first, into f first? F of 1 is 1 over 1 minus 1, which is 1 over 0. This is undefined. And so we can't compose f inverse composed with f of 1. This doesn't work because this right here, whoops, I erased it. This right here is not in the domain of f. Okay, so if we can kind of sum this up here, basically the big point here is that if you have a function and its inverse, the domain of the function becomes the range of the inverse, and the range of the function becomes the domain of the inverse. And this sort of makes sense because, as we've seen before, we have those two graphs that look like this. This is f inverse, and this is f. The x values turn into y values, and the y values turn in. Really made this diagram as complicated as I can now, but the point remains. The inputs become the outputs become the inputs, and so the domains and ranges reverse. All right, so one more problem here, or I guess one more example. Let's find the inverse of 1 over the square root of f of x. So to do this, let's first think about the range of f of x, or sorry, the domain of f of x. The domain is anything except for 0, so you can either write r/0, or this is kind of a fancy way of saying it, or you could say all real numbers except x equals 0. And the domain, or sorry, the range, is the set of output values. And if you think about this again, we have sort of the same situation where, as the last one, if you put in a really big number or a really small number or something close to 0, you're going to see that the only value you can't get out is y can't be 0. So any of these ways of writing this, you can say r minus 0 or r just remove 0. You can say all real numbers except x equals 0, or you can say something is not equal to. And all of these are sort of similar ways of saying the same thing, but they're all legit. Okay, so now we have the domain and range of f of x. Let's think about the domain and range of f inverse of x. This is going to give us the same result, and the reason for that is because the range here becomes the domain of the new function. So x cannot be 0. And the range of the new function is the same as the domain of the old function. So the range here is y can't be 0. Remember that we're flipping the x's and y's, so this is confusing because the inputs of a function are the domain, but they're always the x values. And so like the domain is always going to be values of x, but we take the range of the original function and make that the domain of the old function, of the inverse function. Okay, I know this is a lot of stuff here. I want you to go through and try to find the inverses of these two functions first, and then I'm going to go through how I would do it. Okay, so let's start with the inverse of f of x over here. We're going to flip the x's and the y's. So we would have y equals x plus 1 squared. We're going to change the spots where the x's and y's are. So we're going to invert by switching the x's and y's squared. Okay. Now we need to solve for y. So we're going to take the 2 square roots of both sides, or just, I guess, really the square root. So we have that square root of x is equal to y plus 1 now. Normally we would have plus or minus here. And then if we subtract 1, we get y equals this plus or minus square root of x minus 1. Now, normally we say this is the inverse of the function. So this is the inverse of the function. But the inverse function is just the positive square root of x minus 1. The reason for that is because if you take a look at the graph of this thing with the plus or minus, it'll be a sideways parabola and it fails the vertical line test, so it's not a function. So that's sort of a throwback to hopefully first semester. Hopefully you remember that from there. If I'm being honest, I should probably label this one also. This is the inverse function. If I'm being honest, I'm going to accept either one of these this year, just because we don't really have the time to be as specific and be as picky about this type of thing as I might normally be. So we're gonna go with either one of these as our answer. Know that there is a difference between the inverse of the function and the inverse function. This one is the inverse function. This one is the inverse of the function. So that's the sort of weird stuff there. Okay, the other one. Other one is a little bit more straightforward. And so we have y equals negative 1/5 x plus 2. Okay, we're going to invert by reversing the x's and the y's. and then solving for y. Okay, so minus 2 minus 2. We have x minus 2 equals negative 1/5 y. And then we need to multiply by negative 5 on both sides. Okay, so now we get negative 5x plus 10 equals y. And what are we left with? Okay, so y is equal to 10 minus 5x. This is the inverse function, inverse of the function. And since this is just a line y equals mx plus b, and it's going to look something like this, this is a function already, and so we can just say that the inverse function of x is 10 minus 5x. Both of these are the same here, but this is the inverse function. It's in function notation. So this is really the inverse function. This is the inverse of the function, but they happen to be the same in this case. All right, so that's a lot of stuff there, and I realize that. So I'm going to give you kind of a limited amount of practice problems today to try, and then you have a mastery check to get done, and then you are done for the day.